again new topic. We will look at some important continuous valued random variable. I will do it in two parts because there are a number of random variables that you will encounter in nature. Okay, simply going through all of them may be a little bit tiresome also. So I will introduce some 5 or 6 now. Again later we will take something more. Okay, for example, we saw HED distribution and then HED random variable and hyper exponential. Okay, gamma also we have seen. We will look at some more things. Later on we will see things like Weibull. Probably I will at least touch upon alpha, beta, Weibull, and then Pareto and so on. So they are all coming up later. Now let's look at, let x be a random variable, okay, which is standard normal, having a standard normal distribution. Okay, we will look at a random variable y which is equal to x squared. Okay, yeah. So this is the random variable which you want to look at. So what will be the distribution of that? That is fy of that. This is what we are interested in. So for that what you have to do is, this, if you look at it, there will be 2 values of x. First we have to, in order to find out, we have to find what is the inverse function which maps out to inverse. Given a value of y, what value of x will correspond to y? Okay, so then we can see that if you want to find fy of y, you have to find those x's, okay, for which will correspond to this one. At each of this one, we have to multiply it by the Jacobian of transformation and then do it. So this is how we have been doing. That is, find those values of x for which will lead to this value of y. Which on squaring will give you this value of y. And those x's we have to evaluate fx of x. Let there be 2 values. For example, we can find out. So there are 2 values of x for which this will be true. That is plus root y minus root y. Okay. So if you put plus root y or minus root y, you will get a given value of y. So this will be equal to fx evaluated at plus root y plus fx evaluated at minus root y. And each one of them you have to multiply it by a Jacobian of transformation. What is that one? That will be mod of dx by dy evaluated at x equal to plus root y. Here again dx by dy evaluated at x equal to minus root. So this is what we have to do. Well, first we will look at this dx by dy. So x equal to plus root y. So if we have, then will be, that is this y power r. So 1 by 2 into root y. This is what will be. So 1 over 2 root y is what is dx by dy will get. Whether it is for minus, once you take the mod, the dx by dy mod will be the same for both. So you got the Jacobian of transformation. So you have to put it in these 2. So fy of y equal to fx. So first of all, what is x? X is standard normal. We will write down the corresponding density function of SDN, which is 1 over root of 2 pi into e power of minus x squared by 2. So we have to find fx of plus root y. I will write it For both of them it is the same. So if I put plus root y here, then what do I get? E power of minus y by 2. Minus root y if I put, then also I get y by 2. There are two such things which are similar, or we will write it. So that this is twice and this goes away. This minus root y and this I can club it, and then I can write it like this, e power of minus y by 2. This is what fy of y means. Okay. So this is called as the chi-square distribution of degree 1. Okay. So this is an important distribution. What is it? It is just a square of a standard normal randomly. Then we have another thing. If x is n01, y is n01, we saw that x squared is chi-squared of degree 1. Similarly, y squared is also chi-squared of degree 1. Now we will define a random variable there which is x squared plus y squared. You can follow similar steps and then find it. We will not do that. So this will again take a form that is called as the chi-square distribution of degree 2. And in this manner you can also have many random variables, 3 random variables, x squared plus y squared plus z squared will be chi-square distribution of degree 3 and 4. They all will be of use. Then one more thing. If suppose if we define z to be root of x squared plus y squared, that x is n01, y is n01. Okay. Of course, I think they have to be independent. Okay. Then this we have already encountered. Then z has what is called as the Rayleigh distribution. This we have already seen. Okay. I looked at we define x squared plus y squared, and then we where x and y are standard normal, we derive the distribution of the magnitude x squared plus root this r and theta, both of them we got, and we told that z has this the r, the radius, okay, in polar coordinate will have Rayleigh distribution. You will encounter this Rayleigh distribution quite often in communication system. Okay, later this will be. Okay, then this is also something which we have seen. Let us look at random variable theta, which is uniform between minus pi by 2 and plus pi by 2. So this is theta. Okay, and then we will define a random variable x is equal to h tan theta. We again encoded it because I wanted to specifically emphasize this Cauchy. It's called as Cauchy distribution. That is why I am again mentioning h tan. We are interested in finding the distribution of x, which is h tan theta. So how do we find it? First, in order to find that one, we have to find the inverse method. Given a value of theta, we want to find, theta, the fx of x. So we want to find, given a value of x, what theta it will correspond to. And then we can plug it in f theta of theta for those. So we can find that tan theta is equal to h tan theta is equal to x. X small x. Okay. So this is how it will correspond to. Between minus pi by 2 to plus pi by 2, I think there is a 1-to-1. There are no transformation between theta and x. I think you guys would be better knowing this. Am I right? Between minus pi by 2 to plus pi by 2, for every theta, there will be a unique tan theta, and therefore x is also unique. Therefore, you don't need to find two values. Only thing is, for this x, I find the theta. Fx of x is equal to f theta of theta at that theta corresponding to this. Only thing is I have to multiply it with the Jacobian of transformation. So, fx of x is equal to f theta of theta at theta is equal to tan inverse of x h into the Jacobian of transformation, modulus. What should come here? What Jacobian of transformation? It's some d by d, that is known. Whether it is dx by d theta or d theta by dx. Huh? How many say it is d theta by dx? Raise your hand. How many say it is a dx by d theta? Please raise your hand. And you have to raise your hand for either one of these. Please raise your hand. The friend. It's nothing wrong. This is the time you have to. It's very simple. If you want x to y, transformation is there. Then fx of x dx is equal to fy of y dx. This is what the basic thing. That is, fx of x you evaluate over an interval dx. That interval maps to some other interval dy. It may not be of the same length. That is because this transformation will stretch or compress. Okay, the curve. That is, for this dx there will be some other interval dy that will get. So this, if you want to do this one, this is the probability that it will be confined, okay, in this interval of length dx in x lie between x and x plus dx. This is y lie between y and y plus dy. Assuming 1-to-1. If there are many, for each one of these x you have to find it. That's it. So this is the way you remember this. This is very important. So this holds good. Very simple. Okay. Then in that case, if you want to find fx of x, it is fy of y into dy by dx. If it is fy of y, it is fx of x into dx by dx. That's all you have to do. So what you are doing here, immediately d theta should come here and dx should come here. That is why dx will go and then the equality will be by 2. So you don't need to worry about, there are two Jacobians I have mentioned, j star or j inverse. What to multiply and all, you don't need to have any confusion. It is is what you should, what you will get. Well, then first we will find this one. Okay, so we have got this. Then what you have to do? So this we are going to evaluate. F theta at tan inverse of x by h. Into anyway, I will put it like this. So what is this value? Sure. Yeah. Just because it is uniform. Whatever complicated thing it come, I don't care. It is uniform. Between minus pi by 2, it is true. Okay. What is the range of x? Minus pi. Huh? What values x can take? Minus infinity plus infinity, because so this is 1 over pi only. So this is the so-called Cauchy scheme. So we have seen chi-square distribution of degree 1, 2 and so on, Rayleigh distribution, then Cauchy scheme. Okay, fine. I'll finish one more and then we will discuss about the physics. Log normal distribution. Okay. X is said to have this. You can draw Ln or something log normal distribution. Here, log x is standard normal, has standard normal distribution. A random variable x is said to have a log normal distribution. If you take log of that random variable, that will have a distribution. So whichever random variable whose natural logarithm has SDN is called as the log normal distribution. So we will call this u is equal to ln x. We know u as standard normal distribution. What does that mean? Fu of u is equal to 1 over root of 2 pi e power of minus u squared by 2. Right? Then we have to find fx of x. Is fu of u evaluated at that u for which it need not be specific, okay, we will generalize. We need not be standard normal. It has to be normal distribution. It can be of any distribution. Then in that case, what will happen? This is not necessarily standard normal. It can be any arbitrary one. Sorry. Then U is ln x. Into you should have du by dx. So we have but x will be greater than or equal to 3. Huh? That's okay. So that is the log normal distribution. Yeah. We will stop with respect to the different distribution at this point. We will encounter some more distributions later. Then we will take up some more theorems now. Before that, there is a request that the quiz be shifted from Monday to Tuesday. Okay? Huh? Pardon? No. Who gave the request? There are someone told you by now you would have got many requests that it has to be shifted. I got only one that one request, and then you sent one more. This one. That request came for some reason. Because the lot of quizzes are coming out one after another, we need time, so you need to wait. Your thing was for some IIT
Monday
sports.
they are going to represent IIT Madras.
How many? How many are going? Come on, I say some other people are going. We can't do anything.
Oh.
So you tell me now.
Already gone.
Huh?
Like they're already gone.
But how many are? At least you have some idea. They might have gone. But how many? Well, right now that is few people. How many? We have our quiz scheduled on Monday. And when do you want it to be shifted?
The next day or like
Tuesdays. Tuesday is a working day, right?
no. Wednesday is a holiday. Tuesday is a holiday.
Tuesday is a working day. Wednesday is puja. No. So how many want? You others also may have an idea of going for clubbing holidays and so on. I don't think anybody really is keen about that one, so we will have it on Monday.
But
Yes.
we're going to Training Trichy today.
Huh?
We're going to Training Trichy today. Some people have already left today.
Okay.
So we will be coming back on like Monday, Sunday, 8 night of
On which Sunday?
2nd October, yeah.
Okay. You will be coming, yeah.
Late night.
You have enough, whichever way you are coming, flying or by train, I think you have enough time to read during that time. I will be coming like that way. Okay. Yeah. Certain powerful theorem. Okay. Indeed, if you look at the general probability landscape, all these things, there is one theorem, central theorem called as the central limit theorem, which you cannot miss it, and that is the very that is what actually made the application of probability theory and the usage of the Gaussian random variable so popular. So to this we will look at three theorems. One is called as the weak law of large numbers, another called as the strong law of large numbers, third is the central limit theorem. Incidentally, I will show happen that I will not get to, I will state it, from that it will become very, this one we will not rigorously prove them, only we will apply. So what we are looking at is, we are looking at a random variable x, okay, and then we will look at a number of realizations of these random variables. We will denote these as x1, x2, x3 and so on. Large number of realizations of these random variables. Or the other way is, we have IID random variables, x1, x2 to xn. And each one of these you get a sample, which is xn. This random variable has a characterization. We don't know what the characterization is. It's fx of x or something which we don't know. Therefore, we don't know its mean or E of x. We would like to predict. We know that there is a random variable, and or every time you take a realization of it, or if you treat each one as a separate random variable, and then take the realization. With the help of these things, you want to predict. Actually, we are trying, now we are getting into what is called as the statistics. So far, what we have been looking at is probability. The difference between these two is that in probability, we start applying the probability axioms, probability triple, which we started off in the first lecture. That is, you know the sample space, okay, you know the what all events that can occur, the sigma algebra is also constructed. Then we know the probability measure for each of this event. To become a little sophisticated, we associated a random variable, and we tell with using this probability triple, the probability that the random variable takes a given value or takes a value in a given range, depending upon whether it is discrete or continuous and so on. So the basic probabilities are given to you. Once you know that one, you find mean, variance, all these things, you transform it, you have 2-3 random variables, you look at their dependence, independence, all these things, everything follows that. But now the question is, who gives you the probability? It is given, then right now you are now very conversant in working with that characterization of a random variable, which means that its probability, the random variable takes different values are given to you. With that, now you can do many things. But first of all, how did you come into got those ideas, probability that x will take a given value and so on. And that is all statistics all about. To construct the probability model, to find the probability measures, that is the whole thing, statistics. Once you have used the statistics principles and get that one, then you can apply probability and do that. We are doing the other way. Once given, we are looking at the various ways of handling the random variables, nature and so on. So this is sort of a first introduction to that statistics. Mean E of x is what we want to make. So here what we would like to do is, so for example, you have a coin, let us start with a very simple thing. You have a coin, it's a biased coin. The probability that head comes is not necessarily 1/2. It can be 0.3 or 0.7 or so on because it is weighted. You would like to find out what is the probability of hitting. What do you do? What will you do? By looking at a coin, you don't know. Something is, it is being manufactured such that it is biased. Looking at it doesn't tell whether a head comes or tail comes. Or we have an opinion poll. There is going to be a assembly poll that is going to be held. Different people are talking about party A will win, party B will win and so on. You don't know. You ask someone tells party A is likely to win. Someone. You don't know. What do? You can make an opinion poll, ask few people, collect the opinions and then guess or construct some methods and so on. Here what you would like to do for that coin is toss it a number of times. I will toss it 100 times, and if 65 times head comes, then 65 and 100 can be used as a measure for the probability of occurrence of head. That's a very non-common sense way of treating it. That is what we are going to do. So these are the sample values. Then we will find the sample average. That we will call it as MM. M because it is going to stand, it is going to eventually, we are going to interpret it as mean, that is why M. And this averaging process uses N samples. That is why this N also I put it, because if N differs, then its behavior may be different. With the 10 tosses, if you try to guess, it may not be good. If you make 1000 tosses and then try to guess, it's likely to be better. So N is large, the better it is. That is why I also remember that N and putting it this one. So what is this N? How do we measure a given M? See, this is MM. If I do N tosses, N realizations, and then find the average of it, I would get x1 plus x2 xn by m, and that is a value which we call it a small m. So again, this itself is random, because once you do 100 tosses and find an average, I will get one value, 0.65. Another time I may do and I get 0.72. So again, this itself will be random, which means that I can define a random variable which is a sample mean random variable. That is x1 plus x2 xm by m. So what is this? This is one random variable, this is another random variable, all these things, they are all IID random variables. I define another random variable which is called as the sample average or sample mean random variable, which is sum of these random variables divided by m. And this m1 is going to be random. And one value we can take is what is given here. If one of the realization is small x1 to small x1 divided by n is one value taken by you. Okay, this is what I would like. I would like to use this random variable to guess, okay, this mean here. This is what I would like to do. Now we will investigate the behavior of this random variable m. So you can find the expectation and variance of mn. So what is mn? It is x1 plus x2 xn by n. So what would be the expectation of mn? You can apply the expectation on this side as well as this side, and then use the principle of linearity of expectation. Expectation of sum of random variables is the sum of their expectations. And any other constant that you have, if you have two things, we will use this basic thing. This we know. We also know that variance of a times x is what? A squared times variance of x. And variance of x1 plus x2 is something is to be mentioned. They are all independent. Covariance, yeah, they are all independent, so I don't even bother about covariance. So we are going to make use of this basic results. So E of m1 is E of x1 plus E of x2 by n, where xi are IID random variables. Therefore, all this will be the same. It is n times E of x by n, that is equal to EF. EF. Let me give a name for that. The usual conventional name, which is mu. I think you remember this symbol. It's the definition. I will define this to be mu. So, and variance of x also. So, E of x, we will denote it as mu for convenience. Variance of x, we call denote it as sigma square. So now, how about variance of Mn? Okay, so there are n of these. So it is n into variance of x by n squared. That is equal to sigma squared by e. Okay. So what happens here is that the beauty of taking the sample mean is that the mean remains the same as the individual mean of the IID random variables, but the variance becomes lesser and less. Variance becomes 1 by n times the variance of the original random variable. Okay. So what does that mean? So if you have, for example, E of x, some curve like this, not necessarily Gaussian. It's something like this one. This is the mean. If I take two of them, add it, it will also have mean like this one, but variance will be less. What is the interpretation of variance? It is the spread of the distribution. That spread will be less. It means that it will be less, something like this. But in order to conserve, it will become like this. And if I take more and more n, the variance has to be less. Why it is? Why it has to be x minus mu the whole squared expectation. So from whatever x that you get, it has to be like this, because whatever x that you get, you find the difference and square it, okay, and then take the expectation. So that becomes lesser and lesser when n becomes large. That will happen only when whatever x that can be realized will be very close to the mean. Because the moment you are doing it this way or that way, you are squaring it and then taking the average of it. Expectation is average. So variance reducer means it has to be more and more concentrated at one point. Okay? It will become more like a direct delta function. So this is what the density function will Mn will look like. So if you have a random variable which is like this one, okay, then what will happen is it becomes more and more deterministic. That's what what is a deterministic variable is when one way a random variable which has the mean equal to the value that the deterministic variable takes with variance equal to 0. So that is where it is converging to. So in the limit n tends to infinity, Mn, okay, will become so this is not a lot, please don't write. I am just telling you to give an interpretation. We will make it more precise. Now, that is what you know by looking at this one. But we will make it more precise by applying the Chebyshev inequality for Mn. What does that say? M1 also has got a mean of mu. Probability that M1 deviates from the mean by some epsilon is equal to, is less than or equal to, exceeds an epsilon. We will write it in form M1 minus mu probability greater than or equal to epsilon is less than or equal to sigma squared by epsilon squared. This is what the Hebbian inequality tells. So this is true for any x. In our thing, this is put it that it's not for any x with a mean mu and sigma squared. This is what is true. We will apply it for M1. For M1, what happens is its variance is sigma squared by n. So which means that in the limit n tends to infinity, the probability that M1 deviates from the mean, okay, by any value epsilon, which however small you take, okay, that probability becomes less and less because as n becomes larger. As n becomes very large, this probability becomes, it will be less than this. You can take sufficient value of n so that this quantity becomes 0.001 or something like that one, which means that M1 can deviate from mu, but those properties, okay, and you can also take sufficiently small value of epsilon, will be less than 0.001. That is, in certain realizations, you might have, what it tells is, there may be a case where M1 may be different from mu. That is, you take 1000 realization, 1000 times you toss a coin, and then if probability is 0.4, you should get 400. Sometimes you may even get, most of the time you will get 400, 390 or around that only. Sometimes you may also get 700. But the probability of getting those values which deviate from this by some value 10 or so, that becomes very, very small. That's what this weak law of large numbers is. So to give an idea of what it is, we will consider an opinion pool. That is, we have, so let's say, an election in some constituency, and you are asked to take an exit poll. You might have seen many such exit polls are being discussed in many English channels these days. Then what is, there is a science, of course you know that there is a science behind all these things. How many samples you take, how do you sample and all those things. How many samples you don't get into. They have to find representative populations or based on their geographical, linguistic, caste and all those things, dirty things are there. You will only look at from the statistics point of view, assuming that there are all the populations equally like you. Okay? How much sample you should take in order to get some statistical method with certain confidence. Let us say what you do is you have a population wherein each one of the entity is you are going to ask the question and the entity will tell yes or no. So you see, maybe there is a party here, you would like to know, okay, what is the percentage of vote they will get. You expect if they are going to get 50% of, let us say 60% of the total casted vote, you are going to tell that party is very likely to be. So each one will going to give something. Okay? And if all are identical, we will make it simple, all are identical, if that is what is going to happen, then this person will tell with probability P is equal to 0.6 that he will vote for party A. With Q is equal to 0.4, he will tell I will not vote for the party A. This is what is going to happen. Once you know P, you are done. That's all these things. Okay, 6.6 means 60%. You don't know this before taking this. So, what you know is, so you are going to, let us say, ask some n number of people about the opinion, and then ask whether construct, give estimate P based on that. So what you do is, for n number of people you ask the poll, you give a 1 if the person says yes I am going to vote, 0 if the person says I am not going to vote. If that is the case, M1, that is x1 plus x2 xi by n you are taking. What is x1? Xi in general. 1 means 1 with probability p, 0 with probability 1 minus p. That is, 1 says I am going to vote, the probability is p, which is not known, and so on. And this quantity, whenever it is 1, it will be, and then this way, M1 will directly is a measure of it, that you should be able to get control. Okay? Because this is n, wherever you are going to say yes, this will be 1. So if 60 out of 100 if it is there, then it is 0.6. So this is what you are going to use. You are going to use M1 as this. So in this one you can see that x is a Bernoulli random variable with probability p, and p of x is p, and variance of x is p into 1 minus p. So if you apply Chebyshev inequality, probability of M1 minus mu is greater than or equal to, let us take the case that you are going to look for an estimate for p, but you cannot find the exact one. You are ready that the p value can have a variation of 0.1, can deviate by 0.1. You are ready to that. With that you want to be. That is M1 minus the p. Okay, that's what you are going to. M1 minus p is greater than or equal to 0.1. This will be less than or equal to how much? Sigma squared by 0.1 the whole square into n. That is very important, because it is a sample average. What is sigma squared? It is sigma squared of the Bernoulli random variable. Individual random sigma squared is the variance of the Bernoulli random variable. Once you take the sample mean, it becomes sigma squared by n. That is what we have seen. So, and this is the epsilon squared. So, what is sigma squared here? You don't know p itself, you can't measure. But p is 1 minus p. So, this you don't know. But the best thing that you can do is, you can give what is the largest value it can be. Okay? The largest value of, what is largest value of variance of a Bernoulli random variable? Huh? So it is 1 by 4. In order, that is with the largest value it can. So if you take n is equal to 100, that is you take 100 people in a big city constituency and then take a vote, then you will get 1 over 400. This is, you will get 1 by 4, which is 0.25. Okay, and this is probability of M1 minus p, the greater than or equal to 0.1. Look at, this is a very crude way of doing opinion sample. We will interpret what it is. That is, p can vary by 0.1. If the actual value of 0.6, I am ready, that is, you tell the party A will get 60% of the vote, I am ready with a variation of 0.1. That is, it can go from 50% to 70%. If for that to happen, then the probability will deviate from, what it does is, probability that in an opinion poll, the percentage that I find p, and in terms of the percentage that I measure, goes below 50% or goes above 70%, that probability is less than or equal to 0.2. That's what it is. But if it makes this kind of a range wide variation beyond 10% from this one, you can't make any prediction of winning or losing. Okay? And even then, that it's also possible with a high probability of 0.25. Okay? So we have to do something better. So for that, what we will do is this one, not 10% variation, I am okay with that. I am just looking at 1% variation. What it means is, let us say a party A is going to get 43%, okay? 42 to 44% is anything if it happens in opinion poll, it is okay. For that less and this, for it to go beyond these things, that probability has to be very, very small. Then I have confidence or no opinion. That is what we are trying to do. And that has to be less than, again you will put the same number, 4 into n into the whole square. And what should be, this one I want it to be again very small. Okay? Of the probability is again, I can tell this should be of the order of 0.01 or so. Okay? That is with 99% or 0.05. With 95% accuracy, I want to predict. That's what it means. That it can deviate from this, it can deviate from this range. Okay? With only 5% of the time only it will deviate from this range. 95% of the time, when I make an opinion poll, I will get a value in this range from which I will tell it is 43%. You can plug in values for these things. For the same thing, you will find that n is equal to something like 50,000. A similar problem is worked out in Betsigas one. This is what we do. Okay. This is a very good way of doing, but you see that your opinion poll now tells that you have to make an opinion of 50,000 people, which is again meaningless. In a constituency of 2 lakh people, if you are going to make 50,000 people, it is very so that is the weak law of large numbers. Okay. So we will stop at this point.